Hi everyone. This video is going to cover the material in chapter 2 of the AP Chem textbook. So again, this is a lot of the fundamental information, the things that we've been covering in the past. Now, this chapter spends a good amount of time, several pages in the beginning of the chapter, looking at the history of the atom, talking through Thomson and Rutherford and Dalton and all that stuff. I've chosen not to cover that within this video because the AP exam itself doesn't really touch on that. But if that is something you're interested in, if you do have a passion for history, I would suggest reading through those sections. Give yourself a deeper understanding of how did all of the ideas of the modern atom come about. So if we take a look at the nuclear atom, what we are looking at today, the nuclear atom contains a very small, dense nucleus, which Rutherford postulated as being contained by protons. We now know it also has neutrons in there. And then outside of that nucleus is where the electrons reside. We know that they reside in specific orbitals, and you can see here by the image, the size of that is going to vary quite a bit, right? The electrons occupy a much greater range than the nucleus does, although most of the mass of the atom is in that nucleus. So we've got the three particles. We've got the proton, the neutron, and electron. Proton has a positive charge, electron is negative, and neutron is neutral. And the one thing to keep in mind between these is that the proton and the neutron have about the same mass. It's slightly varied, but essentially they're about the same. But comparatively, the electron has almost no mass. Right? So if you look, if the mass of a proton is about 1 AMU, right, the electron is more than 1,000 times smaller than that. So that's why when we look at the mass of the atoms, the electrons are often neglected in that, because if you were to bring in sig figs, it's really almost negligible. So if we look at the mass of a single atom, right, like this says here, the heaviest atoms are going to have a mass of about 4 times 10 to the negative 22 grams. Right? That's why when we talk about the mass of the atom, grams doesn't make a ton of sense for us. So that's a big highlighter here is AMU, atomic mass unit. We often talk about the masses of single atoms by AMUs, and 1 AMU has this 1.66 times 10 to the negative 4 grams conversion factor. This just kind of helps give you a sense of scale, right? The masses of the atoms are so tiny in respect to everything else. So atomic weight measurements, looking at this, to try to figure out the mass of these atomic masses is often built through something called a mass spectrometry or mass spec. So to figure that out, that is something we're going to talk a little bit more in detail when we are in person. But the idea is you're sending a sample through, it's splitting it up based on mass, based on charge. And so you can get a sense of, in a sample, how many atoms of varying isotopes will we see. So if we're looking at the isotope symbol, the main heart of it is going to be the element symbol. Remember, the element symbol is either going to be 1 or 2 letters. The first letter will always be capitalized, and if there is a second letter, it'll always be lowercase. And then to the isotope symbol, to the left and up, we see the mass number. Left and down, we see atomic number. Remember, atomic number is the number of protons in a compound. The mass number is the number of protons plus neutrons within a compound. Excuse me. So one notation you might sometimes see is the atomic number. Sometimes it's referenced as Z. So if you're asking like what's the Z for an element, that's just asking what the atomic number is. Isotopes are elements that have the same number of protons but different numbers of neutrons from each other, which also indicate different masses from each other. So we've seen a lot of examples of this. Carbon is a big example, right? Carbon 12, carbon 13, carbon 14. And again, if you're going to name these isotopes, it's just going to be the name of the element. So name dash the mass number. So carbon 12, carbon 13. So they all have same protons, they all have same electrons, different numbers of neutrons. Just a quick reminder, isotopes is not the same thing as ions. Remember, those are going to have two different definitions tied in. So, average atomic mass is something that we look to try to figure out the relative abundance or the mass of the elements based on their relative abundance. So, there's a pretty complex equation here that looks fancy, but what it's really breaking down to is that if I have 50% of an object that's 12, 50% of an object that's 14, my average atomic mass would be 13 because I can average those two numbers and it's equal amounts of 12 and 14. But if I have an average atomic mass of 12 for 75% of my atoms and 14 for 25% of my atoms, so much more of that's coming from 12 that my 12 is going to be more heavily weighted. And so that's where we see this kind of fractional natural abundance. So if I were to work that problem out, right, it would be 12 times 0.75 plus 14 times 0.25. So you get that weighted average. It's the same way that if you're looking at your grades for a class, you might have a weighted average. If the tests are worth more than the papers, you would weight your test scores more heavily, or vice versa. So you have to add up all the isotopes, all their abundances, and that's how you get that average atomic mass. And that's the number that is on the periodic table. So if I look at carbon having an average atomic mass of 12.01, that is the average mass of all of the isotopes of carbon. So here's a sample problem. I urge you to take a second, try it out, and then we will talk it through. So to look through it, boron has a mass of 10. Oops, sorry, switch to that. Has a mass of 10 with a 19.9% abundance. So I'm going to do 0.199, right, to turn my percentage into a decimal. And then boron 11 has an abundance with 0.801 as my fraction. Right? So again, turning the 80.1% into a fraction. So if I do this math, I get 10.801. Yes, I'm ignoring sig figs. But you notice if you look at the periodic table, that's what the approximate average atomic mass is for boron. So that's where all of this is coming from. Now, if you are given a more specific mass than just a 10 or an 11 or a 12 or a 13, use that because that's taking into the account all the slight variations that come from the protons and the neutrons. All right, once we've got all of our atoms and we get comfortable with the elements, here comes the periodic table, right? So we've got periods being in our horizontal rows. We've got groups going downwards, right? We have elements that are named by groups, right? So we know that things like the last column, right, that final group, group 18 or 8A, are the noble gases. Typically, a periodic table is going to have the numbers on top in order, right? Those are going to be your atomic numbers, aka number of protons. Then they will have their symbol, and even though it's not shown here, oftentimes they have their mass. Now, the periodic table you get on the AP exam does not have names. Do not let that freak you out. You guys know the names, you've been using them. They're not going to pull the weird abstract elements. I can't guarantee and say exactly which ones they will and won't pull. I can't say that list is out there, but I've never once had anyone come back to me saying, I don't know the element that they were referencing on the table. Okay, so here it's talking about the periods and the groups that we already mentioned. And here are those group names, right? So we have the alkali metals, the alkaline earth metals, transition metals, halogens, noble gases, lanthanides, actinides. I would just take a few minutes, review this, make sure you are comfortable knowing those names. So when they get referenced, you're pretty comfortable with it. I would take a second to say that this line here, remember, is your Zintel boundary. That separates your metals from your non-metals. Remember, metals are on the left, non-metals are on your right. And let me get a good color here. These elements here are going to be your metalloids. Remember, the metalloids have properties that exist of both metals and nonmetals. Okay, so chemical formulas. Writing chemical formulas, writing chemical equations is going to be the heart of so much of what we do in chemistry. So the molecular compounds are going to be composed of the molecules. They almost only contain the nonmetals. So if you're looking at something and they ask you for a molecular formula, or sorry, a molecular compound, typically that's going to be a covalent compound. It's just another word for it. You've got the 7 atoms that do, or elements that do not exist by themselves, right? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Remember, they will never be written just by themselves. It'll always be H2, N2, O2, and so on and so forth. Couple different ways you can remember this, right? There was the mnemonic horses need oats for clear brown eyes. There was also Hofbrinkel. If that helps you more. So in formulas, right, we have the empirical formulas, which is the lowest whole number ratio of the atoms, and the molecular formula, which is the exact formula of an atom. So previously we've talked about something like hydrogen peroxide. That would be the molecular formula for the compound that we know is to exist. But this is not the lowest whole number ratio, right? The lowest whole number ratio of this would be just HO, right? Because we can divide all of our subscripts by 2. So when we get that ratio, that lowest whole number ratio, that's the empirical formula. The molecular formula is exactly how it stands. Sometimes the two things can be the same, but not always. So sometimes the way molecules are drawn and represented have different names for them. So we know the molecular formula, it's just the atoms in the formula. The structural formula, which is what you see here, is often what we call the Lewis structure. A perspective drawing of that structural formula gives you a sense of shape. So when we go and review our Lewis structures and we look at what's tetrahedral, trigonal, planar, trigonal pyramidal, even now octahedral and trigonal bipyramidal, you will see these perspective drawings come into play. What's in the paper, what's out of the paper. Now, to take those perspective drawings and make them a little bit more realistic, sometimes you get either the ball and stick model or the space filling model. So these, again, show that same perspective. They try to accurately depict the shape of the molecule, but in a little bit more generic form with the drawings. All right, we know atoms form ions, right? So you have 2 different types of atoms here. You've got, or ions here. You've got cations and anions. Cations are when you lose electrons to form a positive ion. Remember, cations are positive, right? Little cat, paw, bad joke. Yeah. So cations are positive. Anions are when we gain electrons, and those are negatively charged ions. You'll see those, the anions, with their nonmetals, and the cations with their metals. The atoms listed on here are the ones that we know always form an ion with an atoms that form an ion with a single charge. Right? Most of them we can find just from looking at the periodic table. Again, hydrogen's a little funky. It can either be both plus or minus. And then we have the three exceptions, right? Don't forget we've got aluminum, zinc, and silver. Aluminum being 3 plus, zinc being 2 plus, and silver always being 1 plus. So again, here's an example of some pretty common cations. We see a lot of these we've already talked about. Some of them, though, are a little bit more complex, right? Some of our cations, like copper, it can be both 2 plus and 1 plus. Mercury, remember mercury does some funky things. If mercury is 2 plus, it is perfectly fine. It's normal. If mercury is 1 plus, it exists as a diatomic ion. So mercury 1 looks like that. You also have one polyatomic ion that is a cation. That's ammonium, because remember ammonia is NH3. Ammonium is NH4 plus. Now for the anions, it's getting a little bit trickier. We've got some pretty common ones that we see that are single atom, but then we also have a fair number of polyatomic ions. You've got the chlorates, the perchlorates, the nitrates, the permanganates, the carbonates, the thiosulfates, all of those. So keep in mind when looking through these first few chapters, review your polyatomic ions. I can't say enough. Your life will be so much easier if you just kind of keep reviewing those, get those back in your brain. I know everyone knows them, but the easier they roll off your tongue, the easier it's going to be for you working through AP Chem. Get this erased. So just what we said here. Know those polyatomic ions. Okay, I don't know why this extra does not want to get erased here. Okay, ionic compounds are going to be between metals and nonmetals. They have the opposite charge, and that's where we really want those charges to balance out with each other. Okay, we're just going to deal with the NH3 in the corner there. I don't know why it's not insistent going away. So when you're writing your formulas, remember you've got the switching phase. So if you have a 2 plus here, right, it can flip over. The 3 from the 3 minus can go over to bring it down here. Now, if you can reduce. So if I have Ca2 plus and S2 minus, right, if we just flip them, we'll end up with Ca2S2, but that's going to reduce down to CaS. Now, when we're naming these, right, if we're taking a look at all of these in general, we've got to look back at if they are binary. If they are binary, meaning there's only 2 different types of atoms, it is going to end with IDE. If it's not binary, meaning there's a polyatomic anion in there, it's going to end just with the name of the anion. We don't have to worry about changing the ending for the polyatomic ions. So there's some patterns to help you remember. Remember, the lower the oxygens it has, it ends up with the ending of ite. If it has more oxygens, it's 8, right? So nitrite is NO2 minus, nitrate is NO3 minus, sulfite, SO3 2 minus, sulfate, SO4 2 minus. And also typically when you have the series, right, the same starter element, you're just changing the number of oxygens, the charge is also not changing for those. So if you can remember the charge of 1, it'll be the charge of the rest of them. Okay, so trying to get some patterns here, right? The charge is going to increase. We've got you're not going to have more than 4 oxygens, for these different rows. Take a look at this. Hopefully this will kind of help trigger some of those memories for you. Okay, so if we have more than 2 oxygens, we've got to have more ways to name them. So instead of just the ate and the ite, right? If you take even more oxygens away, you're going to add the prefix hypo. And if you're going to add even more, you're going to add the prefix per. So perchlorate, hypochlorite. All right, with acids, acids are a different thing. Remember, acids start with the hydrogen and then have some sort of anion to them. So if it's a binary acid, so it ends in IDE, you're going to change it to ic. You're also going to add the prefix hydro. So instead of chloride, it's hydrochloric acid. Bromide, hydrobromic acid. Now, if you have a polyatomic ion, the anion ends in ite, you change it to us. If it ends in ate, you change it to ick. So remember the way to remember, I ate something icky, but I did not bite a mouse. I know it's gross and disgusting, but I ate something icky, right? Ate ick, but I didn't bite a mouse. Ite to us. See? Binary nomenclature, right? This is where we all get to take a little bit of a deep breath because this is just figuring out how many of each element there are for the molecular compounds, right? So reviewing your prefixes here, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, even occasionally deca. You do not use mono on the first one, right? So CO is not monocarbon monoxide, it's just carbon monoxide. The mono only goes in the second one. And remember, if it's a double O, it gets dropped to a single O. And if it's an AO, it gets dropped to a single O. Again, not monoxide or monoxide, right? It's just carbon monoxide, 1O. So if we've got the numbers, we just change it, just like I was talking about. Again, because they're binary, they always end with the IDE. All right. I'm going to give you guys a second. Pause the video, answer the questions, see how these go for you. Right, if I'm working this out, hydrosulfuric acid, because the prefix hydro, it's binary. So it's going to be H2S. Vanadium 2 dichromate. Vanadium's 2 plus. Dichromate is Cr2O7 with a 2 minus charge. So it's just going to be VCr2O7. Sodium hydrogen phosphate. Hydrogen phosphate has a 2 minus charge. So I need 2 sodiums to balance it out. So Na2HPO4. Sulfur disulfur trioxide, S2O3. And aluminum oxide. Aluminum's 3 plus, hydroxide's 1 minus. So I need 3 hydroxides to balance out my aluminum. So AlOH3. Okay, sorry what looks like a break in the video. I have a child who wants to interact with us here. So I apologize if you hear her in the background. All right. So for naming, we got through the first half. Let's do the second half. So now we have second one, silver carbonate. Again, sorry about the child in the background. Second one is going to be oxygen monochloride. Third one's going to be lithium chlorite. Now, this fourth one's going to be a little bit tricky. It's an acid. It's because it starts with an H. It's not a binary acid, so we don't start with hydro. But we got to look at the ion IO3. So IO3 is going to be really close to ClO3, which we know is chlorate. So the ion is going to be iodate. So 8 goes to ic, so it's going to be iotic acid. Now, this last one, we've got manganese. Now we know it's a transition metal, so we've got to list the charge of it. There's 3 oxygens, each with a charge of -2. So -2 times 3 is -6, which means manganese is going to have to be +6. So manganese 6 oxide. Okay, very end of this is when we start looking at organic compounds. So organic compounds are going to be carbon-based compounds. Now, naming organic compounds is a huge, huge field, and it's not something that you're going to have to really get into. But understanding some of the basic nomenclature is going to be really, really helpful. So if you see the organic compounds and they end with ANE, that means there's all single bonds in the compound. Those are called alkanes. Okay. Alkanes again have all single bonds. And if we're just looking at hydrocarbons, they have a really nice formula. So CnH2n plus 2, which means for every carbon, I have twice that number of hydrogens plus 2 extra. Because if we look, right, one carbon with 2, one with 2, one with 2, and then we've got the 2 to cap it off at the end. So to name these hydrocarbons, you just have to name the number of carbons in that chain. Now, if you start changing the ending, it starts meaning different things. So for example, if you have an O-wall ending, that's going to be an alcohol. So methanol instead of methane, ethanol instead of ethane. To give you an idea of what they look like, right? So and most of them have the same prefixes that we're used to, except for the first 4. So the prefixes are going to be meth for 1, eth for 2, prop for 3, bute for 4, and then the ones you're used to: pent, hex, hept, oct, non, dec. Okay. Hope that helps with the naming. Again, you're not going to be expected to do any sort of crazy naming with these organic compounds, but it might be something that you are going to have to at some point adjust to and work with. All right. Let me know if you've got any questions over chapter 2.